Hey, good morning, everyone. So this session is on evolution of astronomy and cosmology by Sathish Chandra. So Satish is an old member of BAS, and he has volunteered with a few of our outreach activities as well. So Satish is back with an interesting talk on evolution of astronomy and cosmology. Over to you, Satish. Please start.
All right. Okay. Thanks, Vishwa. So, uh, good afternoon, everyone, and thanks for joining. So, my name is Satish Chandra. I am based out of Bangalore. By profession, I'm into software. I've been working in the industry for more than 20 years now. Um, but outside, I'm very much interested in science, and always been. Physics and maths has been my favorite subjects. Um, I've been with BAS for close to 5 years. Um, and the topic for today that I thought wanted to talk about was events in astronomy and cosmology. So, there is a certain way in which our understanding of the universe has evolved over a period of time. In the last 2000 years, it has evolved in a certain way, and it has been driven by a number of events. Now, these events were sometimes discoveries, there were theories, there were some accidental discoveries. It's interesting to stitch all that together. At least when I was trying to understand some of it, and I've been trying to do that for last uh, few years now, I think close to 10 years. What I found helpful was just to see if there is a pattern, there is a story that evolves, and that helps us to understand how our understanding has evolved about the universe. So the intention of the talk was to uh, touch upon these topics. We will not deep dive into any of these topics. If there is substantial interest on a particular area, we can do a separate session on that. But idea was to see how our understanding has evolved over a period of time. So we'll not deep dive into any area, but it's more of getting introduced to those subjects and to those topics. So let me start presenting. I have put a presentation in place. So I created this. So, events in astronomy, cosmology. A couple of things I want to mention before we get started. Number one, I'm not an expert in any of these areas that we will discuss. So, my apologies in advance. These are very, very diverse areas. As you will see, there are many, many things that have come together. So, I may be able to answer, may not be able to answer. So, that's one. Because I'm by profession, I'm not like PhD or a scientist. It's more from my interest that I kind of gathered whatever I've gathered. um, Most of the content is from some lectures that I've attended from Stanford University, Yale University, which are open lectures, but also from other talks, open talks, and a few books. The content I've taken is from the internet. So, and I put this presentation in the last 2.5 weeks, and I've not done this talk before. So it's all first time. So my apologies in the beginning if it is, yeah, I've tried to keep the presentation simple and more of pictures, but if it does not, if it looks odd, it's probably because it's the first time and it's been done 2.5 weeks time. Okay, so index. I wanted to quickly list down what are the things we're going to talk about, so that you know what is coming up, and we can pace accordingly. So we'll start off with Galileo's discovery. I thought that's a very good starting point. Where do we start? And as I was thinking about it, this particular discovery has always been very fascinating to me. 1610, we will talk about what Galileo discovered and how it helped in our understanding about astronomy and cosmology in general. Then we'll move on to gravitation, and of course the law of gravitation. This was around the same period, little later than that, later than Galileo. So it's a culmination of work done by Tycho Brahe, Kepler, and Newton. We'll then touch upon general relativity and the cosmological constant. Again, we cannot deep dive into general relativity in the session. Of course, it's a separate topic. It's a very interesting topic, but we'll just see what it, how did it help in what role does it play in cosmology. Then we'll come to Hubble's discovery, and this is going to be an engaging slide. We'll probably discuss a bunch of things here. So that's 1924. Then we'll move on to 1964, where there was a discovery of something called the cosmic background radiation. It's again, all these are interesting stories by themselves if you talk about the people and incidents involved, but we will skip all of that. We'll just come to the bare bone story behind it. So that's 1964. Then we move on to 1980 and the inflation theory, which came about. Then we go back in time actually to back to 1930, and I wanted to touch upon Chandrasekhar's limit and the standard candle and the role it plays in cosmology. This is the only event which is not in the chronological order, but from a story point of view, I thought that makes more sense to keep there. Helps there. Then finally, 1998, discovery of dark energy. So we can touch upon that, and then finally we'll try to summarize. Uh, where are we right now? Discussing all of these things. What is our current understanding of the universe? Yeah. So this is what we have. The first two slides, I'll try to not spend too much time there because I think Kirti already covered some parts of it last time. Um, that some topics are overlapping, but some other topics we'll discuss more. Okay, so let's get started. Maybe we can, from time to time, we can pause and take questions. Not necessarily keep all the questions towards the end. Feel free whenever you have something. Okay, so 1610, discovery of Galileo's Galilean moons. So this, I think, is probably the starting point where we started to really understand what our universe is all about. Of course, at that time, our understanding was this, right? Um, that's Galileo's picture at the right. What I've tried to do is all the slides I have put the pictures to the right so that you can have a view of who those people were. All these people were really great people in their own right, their own area. So this is the picture that we really had. So, and this is what we're going to start off with. This was based on empirical knowledge. Empirical knowledge meaning you go out in the night and see whatever you see is whatever you think it is. So what we see is everything goes around the earth, and it was pretty logical at that time maybe to consider that, hey, looks like we are at the center, everything goes around us. You can see only till Saturn, of course, because people could not see naked eye beyond that. And then after that, you had this bunch of stars which were considered to be static. So these stars represent all the constellations, right? And this was our understanding, and this was the understanding at the time of Galileo. There were some people who were skeptical about this, primarily because of something called retrograde motion. Again, we'll not get into that, but you can offline look at that on YouTube. Maybe there are videos. Essentially, there are planets that go in one direction, but that suddenly change their trajectory, come back, and then go back again. So this model was very complicated to explain retrograde motions. There were a couple of other problems as well, and that led to people like Copernicus to think about, hey, is this the right model? Specifically, Copernicus, he had an idea of, somehow he got to the idea of, if we change Earth to the sun, then the velocities and the motion of planets around the central body becomes more uniform. You don't need to have that circular motion, which which they used to call epicenter at that time, epicircles. Sorry. So there was this set of people who probably thought it's not the right model. Problem was nobody could challenge this because there was no data, there was no evidence to really say, hey, this model probably is not right. And this continued until the time of Galileo. And Galileo actually, he's considered as one of the pillars of physics. About there are three pillars people talk about: Galileo, Newton, and Einstein. One of the things that Galileo actually brought to the table was the importance of experimentation and observation. If you observe something, you have to explain it. He was high on observation, and things changed when he got hand onto the telescope. He did not invent the telescope. It was done by somebody else, but he did get access to the telescope. This is a picture of I think the same telescope which he used, or maybe a recreation of it, but I think this is how it looked like at his time. Very small telescope. Initially, he used this for military purposes. He used it to see, where are the armies coming from, and for the king. And later on, of course, he looked at the sky. When he looked at the sky, a lot of things changed, and I'll not get into the details of all of it because I think Kirti covered some of it last time. But one thing in particular was Jupiter. So when he looked at Jupiter, this is a copy of his own notes from the internet I've taken. So as you can see, he has marked different dates, and this big circle here is Jupiter. When he saw Jupiter from the telescope, he saw these small stars around it, and they were jumping around. They were going from this side to that side. Um, and after consistent observation, he came to the conclusion of whatever this is. Probably he didn't have a clear understanding of what these were. Maybe I'm guessing here, but he came to the conclusion that whatever it is, it seems to be orbiting around Jupiter. And until then, the model was everything has to go around the Earth. So now Galileo had an observation which said that at least there is one object in the solar system which is not going around the Earth, which are these small stars, and which are the Galilean moons, of course, we know today. And now, if there is at least one object in the solar system where something is orbiting something else and not the Earth, what is the possibility that there are other objects also? And then what is the possibility that maybe Earth itself is orbiting around something else? So this gave rise to the Copernican theory in a big way, and this was our first major paradigm shift in our understanding of the universe. This is a real picture when you look at Jupiter from telescope. I'm assuming everybody would have seen it. When I first saw it, it was just amazing. Um, it's when you see it first time, it's really cool. So what do we take away? These finger pointers I put in the end of each slide, which marks what is the takeaway from all of this. How did our understanding about the universe change? In this case, it is heliocentricity, meaning it is the sun that is at the center, not the earth. And we thought we understand the universe pretty well. This continued until the next big discovery, which again radically changed our understanding. It was not very evident at that time, but today gravitation is everywhere. So no matter what topic we discuss in cosmology, gravitation has its own big place there. Gravitation plays a major role. This is the second um, discovery that I wanted to talk about. So gravitation is one of the four fundamental forces in the universe. There are four fundamental forces according to something called the God theory. There's a weak and strong nuclear forces. You have got the electromagnetic force, and then you have the gravitation force. So people talk about Newton. Of course, Newton gave us the gravitation uh, law, but there are a bunch of people involved. So it starts with Tycho Brahe. He was an astronomer, Danish astronomer. He observed a lot of things in the sky, especially Mars, and he documented. It is said that he documented almost 20 years of data. I don't know how far it is accurate, but he meticulously did that. What Tycho Brahe gave us was raw data. First time raw data of the skies, very detailed on a consistent basis. Um, Tycho Brahe actually was of the opinion that neither Copernicus is right nor the old model is right, and he came up with his own model actually, that everything goes around the sun except the sun itself, and sun and the moon goes around the earth. And he wanted to prove that model by his data. So he was gathering all that data, and he was trying to make sense of it. He was trying to see how that data can prove his model, and he wanted a helping hand there. So he hired Kepler as an assistant, and it's an interesting story of how the relationship goes. I'll skip that. Maybe you can do offline reading on that. Um, but essentially, Kepler was an amazing mathematician, scientist, you can say. Um, and he did much more than what Tycho Brahe thought about. So Tycho Brahe passed away after that, and then that is the first time when Kepler got all access to all of his notes and all of his data. And what Kepler thought was he was a proponent of Copernican theory, meaning the sun is at the center, everything else goes around the sun. Now his challenge was to use Tycho Brahe's data and see how the heliocentric model can come out of it. So by the way, this is a picture of the instrument that Tycho Brahe used. Looks like a sextant. There's a scale here. There's a scale here. This is, I think, in one of the Danish museums. I don't know if it is the real one or it's a a remake of it. One interesting thing, by the way, um, Tycho Brahe's instruments were not in the open air. He did not view it at a terrace. It was actually underground, um, because otherwise it used to get moved by wind. So, and then I think he had some kind of hollows in the ceiling. Anyway, so Kepler started analyzing this data, and it is said that Kepler spent another 20 years understanding. By the way, first 4 or 5 years he tried to actually prove Tycho's model. He did try that. He could not, and then he changed, and he finally arrived at the heliocentric model. And it took him almost 20 years to do that. So, what did he do in this time? Is he basically gave us the um, planetary laws of planetary motion, that is Kepler's law of planetary motion. Three very beautiful laws, right? One being this one, where he replaced circular orbits with elliptical orbits. This image is the second law that he gave, which is law of equal areas. And the third one was a more complicated one, which is time period square is proportional to radius cube or something like that. That is what actually then was used by Newton, and Newton was able to resolve a more fundamental pattern from there and apply it to not only the solar system but also our day-to-day activities, apple falling or you throw a ball. And then he could come out with a more fundamental pattern, which was the force of gravity and gm1 m2 by r square, the famous equation. So this was again huge at that time. Probably it was not very evident, but the thing is, gravity is a infinite force. Means it extends until it keeps on going. So it plays a major role in how things evolved after the Big Bang. Okay. Okay. So there was a problem though. Um, there was a problem in gravity in the model that Newton gave, and I'll come to the problem in a minute. But I'll take a break here and see if there are any questions.
Hello all. So any questions you can either put in the chat window or you can unmute yourself and ask Satish directly. Thank you.
Okay. I assume there's none. Sorry. Okay, in that case, we'll continue. So there was a problem in this model, by the way. Okay, and the problem was that the force of gravity was actually a force at a distance, meaning um, the problem was this. The equation says force is g m1 m2 by r square, but when the masses are not in contact with each other, when they're not touching at all, how can they exert force on each other? It is probably, according to one of the standing ideas, was that you need to have a contact to have any kind of force. So how can uh, two two objects exert a force on each other when they're not at contact at all? So this was a problem that Newton could not solve. In fact, in his own book, the Principia Mathematica, he mentions that although it all works fine, how does it actually work at that distance? I leave it to the imagination of the reader. I read somewhere that long time back that he wrote something like that in the book. So I don't know about that, but he was not sure about this until the end. So that brings us to the next evolution and next discovery, next event that fundamentally once again changed our understanding of the universe, and that is general relativity. This came out in 1915, and this actually answers the question that Newton himself was asking, so, as to how objects can exert gravitational force on each other while they're not in touch with each other. So how's that possible at all? Um, Again, GR is a big topic. How Einstein came to those conclusions is a very interesting story, but we'll skip that. We'll directly come to what it says. So GR gives a complete theory of gravity. It explains this problem, right? And what does it say is that space is basically bent. So when we look outside its space, we think, hey, this is just space and it's like flat. But basically, space is bent, and it is bent by matter. So if you put a matter, it can be a star, it can be a planet, whatever it is, it will bend the space around it. And in special relativity, space and time are the same. It's related. Mass and energy is related. So essentially, it says space and time both are bent by mass and energy. So we'll leave it at that. We'll not deep dive into it. But I have a picture that explains this, hopefully, and that will solve if there are confusions what as to what it means. Because this understanding is fundamental in going ahead and understanding the rest of cosmology. So here is a depiction of what we mean here, right? So imagine you take a sheet, it's like a bed sheet, right, and you stretch it so that it makes a flat surface, right? If you take a small marble, not this marble, this is a big heavy weight. Imagine you take a small marble and you roll it on the sheet. It goes in a straight line, right? Now, what this person is doing is he has placed a weight. Maybe it is a little weight, a couple of kgs. What you'll see is when you put a weight on the sheet, it creates a curvature, it creates a bend, it creates a dent in the sheet, right? This curvature is like it's a depression here, so it's a um, the sheet which has got bent in a certain way, right? If you were to take a small marble now and repeat the same exercise, you throw it in a straight line. This time we will see that it goes in a straight line, but when the curvature starts, it starts to fall into the curvature, which is very it's common. It's from common sense. I think we can figure this out, logically speaking. We've seen this many times happening. So, and that change in the trajectory of the marble is because of the curvature change that's happened on the sheet because of the weight, right? This is exactly how gravity works. The sheet represents the space, and the weight represents the objects like the sun and the planets, right? Now, if you roll a marble, the marble can be a moon or a satellite, whatever it is. It falls, it goes through, but it starts falling in this depression, in this curvature, and it gets bent. So as a result, what we see is there is a planet which is going in an orbit, and suddenly it changes, and it turns and it bends. In reality, what's happening is the planet is going in a straight line. It has no clue what's happening. It is the space that is bent around the sun, which is creating the illusion of an orbit. It's actually not an illusion, it's a reality, but the reason is different, right? So this is what general relativity explains. So why is it important for cosmology? It's because when people took this idea, um, then you thought about it, when you think about it over a period of time, as more and more data evidence came in, people, it got clear that the universe also has a geometry. The universe is not like that initial picture we saw. It's just that the sun is at the center, and we have a gravitational law. Not only that, it has a geometry, and the geometry can be of three different kinds. um, it can be one of these three, right? It can be something called the center one here. This is, by the way, this picture is it's a two-dimensional representation of the real thing. So, but it, I think, brings out the idea. The geometry of the universe can be a closed geometry, or it can be an open geometry. It can be a flat geometry. Um, we'll come back to this picture later on. I don't think it's relevant right now, but after we look at some other concepts, maybe we can come back to this. But essentially, this is what led to when people started to understand what is the geometry of the universe, because the geometry is what decides how the universe will evolve in the future and how it finishes. So this is what is going to decide that. When people started to do observations to find out, are we living in a closed universe or an open universe or a flat universe, that's how they discovered dark energy in the end. So we'll come back to this, but for now I just wanted to uh, bring up the concept. Okay, So, as a matter of fact, just as a passing idea, general relativity also has a problem. When Einstein wrote his equations predicted that the space cannot be static. So, the space has to either be expanding or it has to be contracting. It cannot be static. Um, but Einstein personally did not like that idea. He was he had his own way of, he was very particular about some things, and this was one of it. He was of the opinion that the universe is static. So to compensate for that, he added a constant in his equation, which kind of nullifies the the expansion or the contraction so that the universe remains flat. He called it the cosmological constant. Nobody knew what this was. This was some kind of a magical constant at that time. All it's supposed to do is to make sure that you have a model where the universe is static, nothing changes, right? And at this time we thought, yeah, maybe now we understand the universe. We have a complete theory of gravity now. We know how gravity actually works. um, we know that there is a geometry. Maybe, yeah, we need to figure out what is the geometry, but overall we have understood, at least for our discussion we can say probably it was clear to a certain extent as to how the universe works. So that continued until the next major discovery that came up, and this is the discovery where really cosmology started, and everything got into a completely different level. So this was the discovery by Hubble. I think everybody would have heard of Hubble. Yeah, a satellite, and I'm sure everybody already knows what he has done. But to set the context, there is a lot of other observations that already happened, which Hubble used um, to do what he did. Okay. The first one was the Cepheid variable, discovery of Cepheid variable stars. It was done by this lady here, Herinta Swan Levitt. I think she also had a team, not sure, but she personally also, I think, went through thousands of galaxies and stars, and these were variable stars. So variable stars are the ones where the brightness of the stars keeps changing. It goes up and down, and there is a time period to it. What she found out was for a particular set of these variable stars, there is a very clear relationship between how the brightness changes and the time period. The time period um, of the star. That means from the time it was bright to dim to bright, right? That is one time period. There is a relation between that time period and how bright that star intrinsically is. That's called the intrinsic brightness of a star. So, if you think about it, this helps us in measuring the distance of a star. So, I would see a Cepheid variable star. I would look at the time period. I'll come back to this graph that she had drawn and look at that graph and understand what is the intrinsic brightness of that star. And then I look at that star using my telescope. One can do that, and that will give me the apparent brightness. And then I compare the apparent brightness to the actual brightness, which is predicted by the graph, and I get the distance. Right. So this is the technique that Hubble used. He looked at M31, which is the Andromeda galaxy, and few other galaxies also. In fact, many other galaxies, I think. And he came to the conclusion that the galaxies are independent set of stars. They are not um, part of the Milky Way. This was one big debate that was going on at that time, because people had seen this nebulae, right? The Andromeda nebulae, the other nebulae, but nobody was clear whether. And people knew it is a bunch of stars, but are they part of our universe? Is that part of our galaxy or some different thing? We didn't know. This was the first time he was able to do this by observing Cepheid variables in these galaxies. And what he finally concluded was these nebulas are completely independent system of stars. Okay, just to give a perspective, right? This image here actually talks a lot. So if you look at this is the Milky Way, right? This is the Andromeda galaxy. So the Milky Way is 100,000 light years, like 1 lakh light years in diameter, right? whereas this distance here is 2.5 million light years. 1 million is 10 lakh. So this distance is 25 times of the diameter of our own galaxy. So when something is 25 times away than the diameter of the object, it cannot be part of this system at all. So this conclusively tells that Andromeda galaxy is a separate galaxy in itself. And similarly, whatever nebulas we see, all those nebulas, wherever there are galaxies, they are all independent systems and they are super, super far away from us. So this was a huge discovery because overnight, I mean, not overnight, but essentially the size of the universe exponentially grew from the time that we initially, the picture that we saw, we thought the constellations is pretty much where it ends. But this discovery showed us that there are millions and millions of galaxies so far away from us that we can't even comprehend. So the universe was really, really big than what we thought. So that is the first discovery. The second discovery was something he did using Cypher's data and, of course, his own observations on top of it. He came to the conclusion, again, an even bigger conclusion this time, that not only these galaxies are completely independent of our galaxy, they are completely different. They are also moving away from us, and not one or two. All the galaxies are moving from us, moving away from us. Um, so this picture here gives that idea, right? So let's say you're standing in the middle. Wherever you see all the galaxies are moving away, right? And if this galaxy is at an x distance, and if it is this galaxy is at a 2x distance, this one will be moving twice as fast. So it's kind of a linear scale. And but the point is, wherever you see all the galaxies are moving away, and there is a, so we can say the velocity with which all the galaxies are moving is proportional to the distance between us and that galaxy, and that proportionality constant is called the Hubble's constant. So huge huge insight that we got here. Now if galaxies are moving away, right, if I rewind back time, if I go back in time, then obviously the galaxies were closer and closer to each other, right, until a time we would reach where everything was at a particular point and everything came from there. So we call that the Big Bang. So this discovery of expanding universe gave us the Big Bang theory. By the way, Hubble's constant gives us the age of the universe. If you look at the dimensions of Hubble's constant, it is uh, distance over time over distance again. um, I think I'll not get into the details of what that means, but basically distance and distance cancels over, and then you have 1/second. So basically, if you do 1/h, you get the age of the universe. That's what Hubble also did. At his time, he had got the value of h a little incorrect. So I think his age of the universe came to, I think, 8 billion years or something like that, whereas now we know it's 13.8 or so. Okay. So one common question people ask is, so where is the expansion happening? So where is the center? In this picture, we have shown a very good, interesting center. So is that where Earth is, or is it our solar system, or Milky Way? Where is this? And this is one of the catches of the discovery. I mean, it's a little difficult to visualize, but essentially there is no center. Um, the expansion is happening everywhere. So how can that be possible? Um, Now I can try and explain that, but I think it's better we use a picture. So I've used a picture from one of the lectures from, I think it was Lawrence Croft, if I'm not wrong, but yeah, probably his. So I've taken it from there, right? So
Satish, can we
yeah,
take questions?
yeah. Please go ahead.
Okay. So there were two questions on the chat from Sunil. So one question was with the previous slide. So what is the equation and orbital movement of Halley's comet? Uh,
Sorry, what is that? What is the equation and orbital movement of Halley's comet? Okay. So Halley's comet. So you have gone back to the second slide. So why I mentioned Halley was the person who actually persuaded Newton to write the book in the first place. And how do you prove that theory? So the force of gravity says gm1m2 by r square. You have to predict. So Newton was able to show the orbits of the planets as of now, but can we predict something that's going to happen in the future? So that was the time when people were talking a lot about comets and all that. So uh, you know there was this comet which Newton proposed. I mean, I think Haley used his equations to figure that out himself, and then he said, predicted that this comet will come back at the particular time. What is the equation? The equation will be exactly same. So you can use basically there is a curve. So the way they do it is you don't start with f equal to m g m1 into r square, but there is a curve which is a 1 by r curve which will show you time versus distance, and then from that we actually predict when this object is going to come back, etc. I don't know if that is your question, or you wanted to ask something else. Sunil, does that answer your question? Hello.
He replied yes.
Oh, okay, cool. Sorry, I didn't see that. What is before Big Bang? So that's a very good question. We'll come back to that when we see when we see inflation. So essentially, the way Alan Guth puts it, he's the person who put he institutionalized the theory of inflation. Essentially, there is no bang in the Big Bang. So the Big Bang does not explain what banged and how it banged and what was there before it banged. According to what we know today, there is no way to know, at least as of now, we don't know exactly what happened at the time of Big Bang. Forget what happened before that. We don't have any clue. We don't even know exactly at the time of Big Bang what happened. We know right after the Big Bang there was inflation, and after that there was a certain time when there was light and everything proceeded from there. But we don't know what happened before that. Having said that, we will look at the summary slide. If we When we get there, there is the our current understanding of the universe is that there are pocket universes, not just one. And so what was there before is there are many universes all the time from the beginning. There is no starting to it. Our universe started 13.8 billion years ago. So we'll come to that when we get to that slide. So where Hubble saw galaxies expanding, is it due to gravity or moving space between them expanding? So that's also a good question. When we say the universe is expanding, um, people tried first to explain saying the space is always there, eternal. It's the ether, and the expansion happens in the ether. But that was finally disregarded for various reasons. What people go with is that even the space itself expands. When we say universe is expanding, space and time, all these concepts, right? There are four fundamental forces in the nature. There are a bunch of fundamental particles which are associated with these forces. There is space and time. All these things got created at the time of Big Bang. So what happened before that? No idea. So that's where our clock starts. Everything comes to being, and then it continues from there. So yeah, so space is also expanding. Yeah. Has Hubble used Doppler's effect to calculate? Yes, that is right. In fact, the Doppler effect was not used by Hubble. It was used by Cipher. So Cipher already had figured out, looking at the galaxies, that there is a red shift that's happening in this nebulae. He did not know that these are independent galaxies, by the way. When you take that data and understand that the galaxies are individual objects by themselves, and he did more analysis on the brightness of those objects, and then he put it all together. That is how he figured out that it's expanding. But that, yeah, but it was basically a redshift that you look at, and then you understand, hey, this galaxy is moving away. Does that make sense? Okay. Any other questions? Age of the observable universe, Priyanka. So that's a good question again. Yes. So our current understanding is it's the cheese model. We'll come to that in the summary slide. Essentially, there are many, many universes, and our universe starts 13.8 billion years ago, and we cannot see before beyond that, because we'll go to the next slide and see we hit a wall. It's called the background radiation. You can't see through that. So the earliest you can see in our universe is that radiation. Universe expansion affects time measurement we observe today. The time measurement. So, okay, that's a very tricky question. Actually, I don't know if I can completely answer that, but I'll try. So, time is relative. Time is relative to how you are moving, to your proper motion. So, we can't ask a question about what is a particular time, because there is no particular, it's all relative. What we can say is, given object A and object B, if you compare both of them and their frame of references, their velocities, then with respect to one object, what is the time dilation you will see when you look at the other object? That is what we can say and talk about, right? That's what I can say. It does not have a direct, at least from what I understand, right, about expanding universe. What expanding universe will do is any light radiation will get redshifted because the this space itself is stretched. Okay. Okay. Any other questions? So the orbital movement, again, that's orbital mechanics is a very elaborate field by itself again. But Kepler's laws are enough to explain orbits. Actually, you don't need to go beyond it. You can explain all kinds of orbits using that, most of it. Right. Okay, should I continue?
Yes, Satish, let's
Okay,
continue.
cool. So where is the center of expansion? These are good questions. Keep, yeah, I think that interesting to see that there are good questions. So yeah, please continue that. So okay, so where is the center? So this picture talks about it. Um, let's say all these dots here represent galaxies, right? These are galaxies at time t1, and these are galaxies at time t2. Okay, and there is expansion happening in between. So sorry, one second. Give me a second. Yeah, yeah. So as you can see, the red dots are actually stretched. It is stretched on x-axis and y-axis both, because the universe is expanding. Now what we do is we say, okay, this universe is expanding. So where is the center? Um, so let's assume we are one of these galaxies. Maybe we are this galaxy here. When we see, what we see is everything is expanding. So what we do is we take this picture and superimpose on this picture, right? And let's see what the effect is. Right. This is what you get. Now this is not a makeup or something. Um, sorry guys. This you can try yourself actually. So you take a piece of paper, you put some dots, take a print, and then again take a print, but scale it up. Some printers have this option of scaling up. Scale it up and print again, and try to coincide one of the dots, the same dot. So if this one is to the second column, second row, take second column, second row here, and put that on top of each, it, you will see the same effect. So if you see, if this is the galaxy, when the person sees from this galaxy, everything is moving away, right? The red dots is where we are now, that is time t2. Also, if you look at this galaxy, this space is much more than this space, right? So that is what Hubble said. The farther you are, the faster they are actually moving away, right? Now you may say, okay, maybe you accidentally picked up the right galaxy here. So you can do this experiment with any galaxy. So if you take this point, you see the same effect, right? So that is what it means when we say expansion has happened everywhere. Yeah. Okay, this actually gives rise to the cosmological principle. There's a cosmological principle which says that our universe is homogeneous and it is isotropic. Um, what it means is when we look at the universe at very large scales, not very small scales, we see the same thing everywhere. Actually, if you look at like 10 billion years into the past, you can't really make out one part of the sky to the other part of the sky. It looks almost the same, and it is almost the same in composition. So that is homogeneity. Isotropic is it looks the same in all directions mostly. Um, that means whatever is happening to one galaxy is also happening with all the galaxies. This principle actually is used later on when people try to discover dark energy. Okay, so this is, by the way, this is the plot Hubble came up with. This famous plot of Hubble. It's a straight line through, speed and redshift and the distance of galaxies. Okay, so huge discovery. This event actually, this discovery completely shifted our understanding. So now our universe is very, very big. And not only big, it has got billions of galaxies. And not only that, all these galaxies are moving away. So that is our understanding now. But there is a problem again. And the problem is this expansion of universe predicts that there was a Big Bang. Now, if there was a Big Bang, then we should see an after effect of that. We should see some kind of remnants, um, thermodynamically speaking, that we can see and measure today. And one of the suggestions was that there should be a thermal echo of the Big Bang as radiation, which should be present even today. People calculated and said there should be some kind of radiation, um, which would be at a very cold temperature, but it should be there if Big Bang really happened. If you imagine at this time, there were a bunch of people who believed in all of this, and there were a bunch of people who did not believe in all of this, even after this discovery that Big Bang really happened. Who knows? So we were missing observational proof. So there was no observational proof of Big Bang. So that takes us to the next point, which next discovery rather, which was an accidental discovery, a very interesting story. You can read it up offline. But these two people made this discovery. These two people here, Robert Wilson and Arnaud Penzias. I keep forgetting the names. 1964. So these guys, what happened was they got hand to the largest or one of the big radio. I don't know if I can call this a telescope, but it was an instrument that could measure radio waves. And initially, it was being used for tracking satellites. And after that, they took over. And it was not being used for tracking satellites. My guess is maybe it was the Cold War time, so maybe they used it for tracking satellites. I don't know, just a guess. But later on, it was given to them, and they were radio scientists, so they were doing radio astronomy. They wanted to look at different patches of sky and understand what is the radio image that comes out. The thing was that when they started to do that, immediately when the first light happened, meaning when you start your instruments, everything is set, the first signal you got, they got noise. They got a static noise, which is not really great if you are a radio astronomer. So they went back and they checked all their instruments. They verified and rechecked and again tried, and they again got the noise. They tried multiple times. They tried pointing the machine at different areas of the sky. They again got that same noise. Um, so they got so uh, confused and frustrated. They actually went into the inside this machine itself, and they found some pigeons there, and they cleared off those pigeons and those nests. Maybe they thought it's because of that. They thought it's because of the city. So they tried every single thing that was possible to try, um, but that noise was still coming up. So, and later on, after I think a couple of months, they started collaborating with other scientists and saying that, hey, we are seeing this weird noise, and that noise is coming everywhere. This was a very sensitive instrument, by the way. That's why it was able to pick it up, and what's going on. And there was the other community of scientists also joined. Apparently there was a different set of theorists who were working on the Big Bang, and they were trying to understand how can we find the proof of Big Bang. People who had predicted that there has to be an echo, so they were looking for the data of how can we get this data. And when they both sat together, they understood that they had made a major discovery. These guys had found out the data that the other people were looking for. So this radiation, apparently it was a radiation. This radiation was isotropic, meaning it was coming from every direction, right? And it was exactly as it was predicted in the Big Bang. The theorists who were predicting from the Big Bang, it was exactly a perfect match. This is the instrument, by the way. These two, I think they are the same people standing there. It was, I think, commissioned by Bell Labs, if I'm not wrong. So this was seen as a big proof for Big Bang accidental discovery, but yet it saved the day. It reinforced that Big Bang really happened. This was such a big discovery that NASA actually spent a lot of money. They sent three different satellites. Kobe was the first. After that, there was WMAPS. I think that right now there is a Planck satellite. Not right now. I mean, the last one was Planck satellite. All the satellites, what it did was their job was to go and look at every part of the sky and take the thermal radiation of the CBR, the cosmic background radiation, and make a map out of it. So that's what they did. This is the map. It looks like an egg, but it's actually a picture of the thermal glow from the Big Bang, right? So this light that you see, so by the way, so this is a graph of temperature distribution. The blue ones are the blue areas are where the temperature is little less, red ones is a little more, but that little more, little less is very, very little. It's actually 1 in 1,000 or so, meaning it is very, very uniform. Everywhere the thermal distribution of this echo is exactly the same, almost the same. And this echo is coming from 380,000 years after the Big Bang. So this is the first time when light started. After the Big Bang, there was a period when there was no light. After 380,000 years, that is the time when the plasma cooled off, and then photons were able to propagate, and everything became luminous. This stage is given a name. I think it's called recombination or something like that. And if I'm not wrong, but this is the first time there was light, and this is the first picture of the universe, and now we can see it. It's pretty extraordinary if you think about it. And the temperature, it is as like 2.7 Kelvin, which is very, very cold, right? It's like this is absolute scale. So 2.7 Kelvin. Okay, so that's what I said. It's a plasma that has cooled off after the Big Bang. um, this discovery reinforced Big Bang, and it ruled out there were other alternative theories at that time, like steady state and others. People now started to believe that it is the Big Bang that is the most closest model. Right? So finally, we have the proof of Big Bang. It was a great step forward, solved all the problems. But like many times in astronomy and cosmology, when we find an answer, we also come across another question, and then you solve that, you come across another question. So that many times happens. So although this explained or gave us the proof for Big Bang, it also came up with a question. The question was, why is the radiation so smooth? Right? um, there is a problem with that also. So that is what is the next discovery, or rather event, I want to talk about, which happened in 1980. So what's the problem? The problem is cosmic background radiation is very uniform, the temperature distribution. And what's the problem with that? I want to explain using some cartoons here, right? So imagine there are four people. Um, they're drinking coffee, and this lady has to pour coffee to all of them. So let's say she pours 4 cups of coffee, and they drink it. Um, Now, what is the temperature at which this coffee will be for all four people? Right? The answer is it's pretty much the same. All four people will have the same temperature of the coffee, more or less, because they're sitting close to each other. Right? But if you scale up the problem, and let's assume you now have a huge area, open area, where a lot of people are sitting, um, and they all sorry, and they all are drinking coffee. And let's assume there is only one person who's serving the coffee, right? Now what happens? The same person has to go here, serve the coffee, go here, go here, go here. Let's say there are 100 people, right? Now if you compare the first person who got the coffee versus the last person who got the coffee, obviously it is very common sense to think that the temperature of the last person would be very less compared to the first person because it would have gone cold. This is the problem we see in the background radiation. The background radiation is something like the second image. You have hundreds and hundreds of people. Imagine this is the cosmos now, right? And because the cosmos is so big in all directions, it's like a huge big party. But wherever you see, you get the same temperature. How is that possible? It's just not possible because you should expect some temperature differences. So that's the issue here. This simple concept led to a discovery, or I would say formulation, of a very important theory. It's a major theory. It's called the inflation theory. um, will not, of course, it's a big area in itself. It was proposed by this person here, Alan Guth. So what inflation in a nutshell does is that it says initially the universe was like the left hand side picture. It's like a very small universe. There was a time when you had, first it went through transitions, phases, right? The first phase was the left picture, then it went to the right picture. So when it was small, it had enough time to have the temperature synced up. And once the temperature synced up, it synced up by the time the next phase transformation started, and the small universe then puffed up into a huge universe. So that is called the inflation theory. So just after the Big Bang, and now believe it or not, 10 raised to the power of minus 36 seconds. So that is the time after the Big Bang, if you can imagine that, is when inflation happened. And it continued for some time, and it increased the volume of the universe in that small period of time by an order of 10 to the power 78. Essentially, people say, if you look at Alan Guth's lectures, he would say the universe was probably size of a pea or a marble, size of a marble at the end of the inflation. And from there, your normal Big Bang continues. Uh, so that's what is inflation theory. There's a lot more to it, but I think for our discussion, I'll keep it here. One more thing to mention is, again, we can skip it, but there's something called omega, which is a density ratio of matter. This omega is what defines the geometry that we were initially seeing, right? Can the universe be a closed or a open or a flat? Omega is what drives that. And part of the problem, okay, what inflation theory predicts is that the omega should be 1, meaning it should be a flat universe. Today we know that it is 1. It's very close to 1. So that's how we know that inflation theory actually is a very strong proponent of what happened. Okay. Um, at the time when this was proposed, the problem was omega when it was measured then was zero point 0.3. That was by observation. And people had to figure out where is the remaining omega, because if inflation theory is right, then the omega has to be 1 or very close to, I mean, at least close to 1. So people said maybe we need to measure distances of really, really far off galaxies, and then we will have a better understanding of omega. And this was also required, by the way, to understand how the universe will evolve, right? How will it end? So to do both of those things, it was important to know the distances of very, very far galaxies. And that brings us to the next topic, which was how can we measure those distances, because there was no tool to measure, right? But I'll stop here for a minute and see if there are any questions.
Oh, yes, Satish, there are a few questions on chat. Very first question is what type of radiation they got in CMB?
Sorry. um, Sorry, Vishwa, I could not hear you.
Oh, yeah. So what type of radiation they got in CMB?
This is radio, in the radio frequency. So it's a microwave actually. So the name itself is cosmic microwave background radiation. So the frequency is in the microwave range. Yeah, does that answer?
Yeah. Uh,
Does the universe expansion affect this? I think we had what type of radiation they got. Okay, microwave and far infrared. Yeah. So this thermal distribution of the volumes. Yes, that is right. So we will see a picture in the end. When you look back to the universe, when you look back at the farthest galaxies, the last limiting point where you can see is this radiation. This is the wall, and this is for our pocket universe only. We cannot see to other universes anyway. At least as of now, we don't know how to do that. But yeah, this is for our universe. That's right. How could they predict the temperature? Honestly speaking, I don't know. That involves a lot of physics. I'm assuming one has to deep dive and really find out what formulas they use. But I'm assuming it will be using thermodynamical laws, entropy, etc., to find out. So what inflation says is there was um, there is an exotic material which is like anti-gravity. It had a certain potential, then it started to express itself, and more of kinetic energy came from there. So you start from there, you work backwards, and probably come to how the temperature should change. But I don't know about that much. Read somewhere before Big Bang there might have been. Yeah, so this is the top concept of eternal inflation. I did not bring it up here, but essentially, there is another problem with inflation. There is a side effect. The side effect is inflation starts actually, but it does not. It should not stop. The reason is, as I said, the inflation was because of some exotic material initially. um, you can say, you can call whatever you want, and it had negative energy and things like that. The point is it decays. Now, why did inflation stop? According to Alan Guth, he would say, oh, it stopped because this material decayed, and after the decay, so this material was not there to push, it was not, anti-gravity was not there, so it stopped. But the point is, if there is a decay, it will have half lives. So it will go half life by half life, and in each of those half lives, the problem is the inflation expansion happens so much that after the half life also you have more of the material than before, right? So that way, once it starts, it should keep on going. So that is why the current model is that of the cheese model, where you have pocket universes. So as to your question, uh, maybe there were universes even before our Big Bang. Yes, that's what we can think of. Fermi bubbles, what scientists have discovered, I don't know actually. So I no idea about that. But since you are saying Fermi, I can take a wild guess here. Um, we do see some changes in the temperature distribution, like we saw in the cosmic background radiation, and that is attributed to quantum fluctuations. If that is something related to this, otherwise I don't know about this. Sorry. Big freeze will end our universe. Yeah. So the question of how the universe will end was is highly dependent on the value of omega, as I said. So if if you look at this picture, okay, so in this picture, right, this is how the expansion can happen. Let's start with the middle one. This is the one where you have a closed universe. A closed universe is when omega is more than 1. That happens when you have a lot of matter inside. When there is a lot of matter, then there is a lot of gravitation. When there is a lot of gravitation, essentially your expansion will stop, things will pull back. So the universe starts to expand, it goes to a point, and then it falls back. So that is how the universe will end. If it is open universe, right? In this model, it starts and it keeps on expanding because there is not enough matter here to actually slow down the expansion. But if it's a flat universe, then it starts, it goes off, and then it tries to reach a point. This is a limit, by the way. It does not go. It's tending. It tends to this number, but it never reaches there. So it kind of is stable. You can say, it gets to this value. Turns out this is what our universe is. This is what inflation was saying, that your omega has to be 1 because of certain things. It predicts that it should be close to 1. Okay. Any other questions? Okay. Very good. So where were we? Okay. So now the problem was when they observed omega, it was zero point 0.3, and according to inflation, it should have been close to 1. And also there was this question of how will the universe end, so and evolve, right? So these are the two things. And for both those things, there was a need to measure how the farthest galaxies were moving. Problem was the Cepheid variable uh, approach will not work here because these galaxies are very, very far. So we need a tool. We needed a tool to actually proceed from here. And that is the next topic I want to talk about. But this happened in 1930, by the way. And this is something called Chandrasekhar's limit. And he was from India, so I think it's something we can be proud of. Um, so I want to quickly talk about standard candles in astronomy. Um, Long story short, what happens is if you look at this image, imagine they're all the same kind of bulbs. When I say same kind, I mean the same wattage. Maybe they are 200 watts or 500 watts. The wattage of a bulb decides the luminosity of that bulb. And as long as your wattage is the same, the luminosity of that bulb will exactly be the same, no matter where you buy from and where you keep it. So if I take the same kind of bulb, right, and I arrange like this, okay, when I look at it, I will look at the first bulb, I will see it as brighter compared to the one that is farther away, right? So by this simple observation, I can understand how far this is because both of them have the same intrinsic brightness. That is the term we use. Intrinsically, they are the same brightness. But when I look at it, I get a dimmer brightness, which is called the apparent brightness. When I take the ratio of apparent brightness to intrinsic brightness, I get the distance to this object, right? So it's a very good way of measuring distances. All we have to do is find a bulb, find the bulb which is like this and which is having the same wattage, and then everything else is simple. And that is what Chandrasekhar's limit gives us. It gives us a standard wattage bulb, so to say, at cosmic scale, right? It's just quite amazing. It's quite cool. So, and how did that happen? So that happens in a particular kind of supernova. It's called type 1a supernova. So it happens when you have a red giant. Again, this will get into astrophysics, so we can't don't want to get to the details of it. Simply put, red giants, I'm sure everybody knows, like very huge stars, and the outside of red giant is loosely coupled with the core because it has expanded a lot and there has been multiple layers inside that collide and things happen. So the outside is a little um, it's not very tightly coupled with the parent star. Now, if this star happens to be in contact with another star which has already become a white dwarf, right? Now, you may say, what is the possibility of this happening? It's actually very possible, because most of the stars we see are actually binary stars, and sometimes more than that. Single stars are relatively less. So, if there is a binary star, having this combination is possible, that one of the star is a white dwarf, one of the star is a red giant. What happens then is, white dwarf, if they are close enough to each other, the white dwarf can start to feed in on the material from the red giant, and this picture shows the impact. So this material flows, and it creates an accretion disk, much like around a black hole, and that accretion disk gathers and gathers until a point, and of course it goes closer and closer to the white dwarf, until a point that white dwarf actually starts to increase in size. What Chandrasekhar found was that there's a magic number after which it cannot take anymore, and that number is 1.4 times of the solar mass. If once the white dwarf reaches that size, that mass, it explodes. And the point is, it explodes with the same wattage at the same intrinsic brightness, and that is what then creates a perfect standard candle for us. Right now, when we look at the galaxies, all we have to do is keep looking at many galaxies, because if you look at one galaxy, you will not find, this is not a very common phenomenon, but there are billions of galaxies. So if I keep looking at all the galaxies, if we keep looking at them, and we see a new light coming up somewhere, we look at the spectrum. If it's an emission spectrum and certain other parameters are in line, then we know it's a type 1a supernova. Then we look at the brightness, measure the brightness, we know the intrinsic brightness of the object, then we can know how far it is. So that is what is used to understand the distance of farthest of galaxies, and that is the tool then which was used after the inflation theory came in, and then to understand how things are going to evolve from here. Just as a side note, just a fun note I wanted to add here. It's an interesting story between Eddington and Chandrasekhar. I leave that in the interest of time to, maybe you can read offline, but Eddington was not initially agreeing to this model, but then later on he did. If you're wondering who's Eddington, he's the one who found out the proof of Einstein's general relativity, that the light bends, and they did that very famous observation during the eclipse. Uh, there's a very interesting story about Eddington and Einstein as well. I would highly recommend to go through that. Anyway, so okay, now we have a tool that can help us in measuring distances of the farthest galaxies. And now with that, we can now go ahead and then see how things will evolve from here. So what we do is we look at Hubble's chart, right? The graph, um, that was a straight line, if you remember, and then we start plotting the same graph for further and further galaxies. So two teams actually started to do that. This is the image of both the teams together. Interesting story is, this is the only time when they got together, when they got the Nobel Prize. This is the time when they actually met. Otherwise, they had not met, and there were two teams were, and there was a race going on as to who will find this first. So both of them were trying to measure distances of the farthest galaxies. Expectation was it will be a closed universe because omega is zero point 0.3, and it is just about understanding, how it, when, etc. it will evolve. Okay. So this is the data that came out. Um, Long story short, what this data actually shows is they were thinking it would be on this line which is going down, or maybe the one that is going horizontal. But what they found was it is on the line that is going up. In short, what it means is, the farthest galaxies are accelerating. They are moving away farther and faster and faster. So until now, we had Hubble's law, which was a linear propagation. So farther you go, the faster it goes. But now you see that these farthest galaxies are accelerating. So Now, this cannot be explained in any way. In any of the things that we have seen so far, there is nothing that explains it. The only thing we can think of is that there is some kind of mysterious matter in the universe which grows with size of the universe, because it is showing the impact in the furthest galaxies, not the ones which are relatively close. That means with more and more distance, this mysterious matter increases, and it has a pushing effect. It pushes on. It's like anti-gravity. And they named it dark energy. So we didn't know what it was, so people just named it dark energy. Apparently, according to calculations, it is 70% of what we see today. 70% of all that we see around is actually dark energy. This comes from the calculation that these guys did from here, which is actually interesting, because 70% is zero point 0.7, and if you add it to zero point 0.3, omega comes exactly to 1. I mean, very close to 1. That is exactly what inflation theory also predicted, that omega should be close to 1. So omega is probably close to 1, and the reason we didn't know was that this dark energy is something which people recently found out. Okay. So the conclusion, we're still understanding what the universe is all about, right? Oh, sorry, here was the plot. So this is the plot that Hubble used. They extrapolated on the same, so on the same plot. So to summarize very quickly, our understanding today. So 5% of all that is around is this matter. So all the stars, planets, galaxies, everything put together is 5% of the matter that is really out there, and 70% or so is dark energy. And then there is 20% or so something called dark matter, which we do not talk about. So in summary, this is how things have evolved, right? So we had a big bang. After the big bang, there was plasma. Nothing happened until 380,000 years, when we got the CBR, the cosmic background radiation that we saw. Um, After that, things started to form, and then eventually we started to have galaxies. Somewhere around 5 billion years ago, somewhere here, I don't know, maybe some point there, dark energy overtook the effects of gravity, and the farthest galaxies started to accelerate. Right. So, so what is our understanding of the universe? As I was saying, this is the cheese model. Um, we think, according to the lectures I have seen, people think that the universe is something like a cheese, and cheese has holes. Each of these holes can represent a universe, and we are in one of these probably pocket universes. Our pocket universe started 13.8 billion years ago. It followed this evolution that is shown in this image here, and that's what we know. And the farthest we can see is the cosmic background radiation. Having said that, there might be other universes as well. So that is where our understanding has evolved to, from the time, if you look at the first slide, it's a huge distance that we have covered. So it's pretty amazing that we were able to figure all this out, but still we don't know what this dark energy is or dark matter is. But anyway, this is the model uh, we think it is as of now. So yeah, so that's what I had. um, Open for questions.
Two questions. So one, it says, uh, I know we don't have a perfect answer for this right now, but based on your knowledge, what started Big Bang? How can everything come from nothing?
Sorry. So yeah, that's a good question. According to what I whatever I know, whatever I've seen, um, we don't know what banged even today. We don't know. All we know is there was a bang, and we can assume that it was because of some kind of an exotic material, um, which had a lot of certain kind of potential. It is called negative pressure, and that negative pressure has this tendency of pushing things. And but where did it come from? What happened before that? I don't think we have a clue about it, but we our understanding starts after the Big Bang. Just right, like 10 to the minus 31 seconds after the Big Bang is when inflation takes over. From that time, we know, but right at the time, we don't know. That's what I think. Maybe the universe started as a black hole. Maybe the universe is just simulation. Maybe it is big contraction. So one thing, yeah, these are interesting ideas. But in my opinion, there are two ways of looking at it. And from whatever I've seen and read, there is a way of looking at this entire cosmology only from observation point of view and data point of view, which is science. And there's also another way of looking at it where you use a little bit of imagination. And there are very serious cosmologists who do that actually. But to me personally, the first approach is makes more things more easy to understand. And at least it gives a it's something which we can follow with. But beyond that, I would say I don't know. But yeah, it may be a black hole or something like that. So yeah, I'm not sure. Thanks, guys. Any relation between uh, dark energy and dark matter are completely two different things. Dark matter we actually discovered using rotation curves when we there was a lady who was observing rotation curves. Interesting story again. She wanted to do a project which is not in mainstream, and she wanted to do something which is not important because she had some housework, etc. I don't know, but so she picked up a project that was not interesting at all, and nobody was actually giving much time there. And she just started to look at galaxies. So essentially, the stars which are at the outermost orbit are also going at the same speed as the stars which are in the inner orbits. That's what gave rise to dark matter. So that's a different topic altogether. Okay, thank you so much. I think those were great questions. I hope this made sense, and thanks for participating. So yeah, if there are any other questions, we can take up. Otherwise, we can wind up.
Yeah, it was a great session, Satish. I particularly like the coffee analogy.
Okay.
How it is in, I mean, it's of the same temperature within a room, but and it's the same temperature even in a big conference hall as well. So that was a really great analogy, and it has actually led me to start diving things into more. And yeah, cosmology is not a simple subject, but you have aptly summarized all the particular milestones. And yes, I mean. Based on the feedback of all the other members, we can actually start looking into individual aspects of that cosmology and dwell into a little bit deeper in upcoming sessions. Yeah, overall, it was a wonderful session, Satish. Thanks for agreeing to take this.
Sure. Thanks, Kirti. And one small comment there. The analogy I used for coffee, that also I took from one of the lectures, actually. I forget whose lecture it was, but I liked it a lot because that really explained, made things clear to me. So most of the stuff I've taken from others. So it's not like, yeah, my own, but yeah, that analogy helps.
Yeah, and regarding the future session links, yes, we have a few sessions that are planned and on bi-weekly basis. Yes, keep on watching out for the Telegram group. We'll keep posting on the information. Yeah.
Yeah. Yeah, in terms of books, some of the books I've liked is there is a book by Michi Kaku. It's called Hyperspace. That's good. By the way, all the books I've read are just they are not academic books. Although I've attended some academic lectures from Stanford University and Yale, which are open universities, but the books I've read are like more of casual reading. But this is very nice book. Also, the first 3 minutes is a great book. Brief history of time. That's also good. The Tao of Physics is good. So yeah, but that gets into quantum mechanics. But these are some of the books. Yeah, but there are a lot of audio video content actually if you look about. So yeah. All right then. Thanks so much. This was great. Thanks for all the questions, and thanks Vishwa, Kirti, for setting it up and you know uh, facilitating. Thank you.
Thanks, Satish. Have a great day.